Okay, welcome everybody. In this video, we are going to walk through an introduction to some concepts and examples from probability that we're going to develop further and explore together in class. So to begin with, I want to define a couple of terms. First is the sample space that we denote with a Greek letter. This is a capital Greek letter omega, and that is going to consist of all of the possible outcomes of an experiment. We're going to let outcome be denoted by a lowercase omega over here. That's what this symbol is. And that's going to denote a single result from an experiment or an observation. And lastly is an event that we typically denote with a capital letter that is descriptive of the event. But in absence of any example, we'll just use A to denote a generic event. And A is going to be a collection of one or more outcomes from an experiment or an observation. So to take a look at an example, let's consider the following situation where you run an experiment where you roll a six-sided die. In that case, the sample space, the set of all possible outcomes, would be either we can roll a 1, we can roll a 2, a 3, 4, 5, or 6. So the sample space consists of all 6 of these possible outcomes. The event A, let's say A represents the event that the roll is a multiple of 3. In that case, we can write A as a set as well. So A is going to consist of all of the outcomes that have a multiple of 3, that are a multiple of 3. That would be a roll of 3 and a roll of 6. So A would be a set consisting of the 2 outcomes, 3 and 6, that satisfy that event. Okay, now that we've talked about sample spaces and events, next we can work with some probabilities and calculate the probability that a certain event would occur. So in probability, we use the notation P of A to denote the probability that event A would occur. And so in the case that we looked at on the previous slide with rolling a six-sided die, we had a finite sample space. There were only 6 possible outcomes. So when we're working with finite sample spaces, we can oftentimes use counting arguments to determine probabilities. And let's take a look at a special case, which is, let's assume that we have an experiment where each outcome in the sample space is equally likely to occur. This is not always going to be the case. We'll deal with sample spaces where some outcomes are more or less likely than others. But in this special case where we have a sample space, such as rolling a fair six-sided die, then any outcome would be equally likely to happen. We'd be equally likely to get a 1, a 2, a 3, a 4, a 5, or 6 on the roll if we assume that the die is fair. Then all of the faces of the die are equally likely to occur. So in those cases, we can calculate the probability of an event by taking what are all of the possible outcomes in the sample space omega. So this notation with the vertical bars around omega means the number of items in set omega. And on top, we would have the number of outcomes that are in event A, so that we could denote with the size of set A. And then the probability of event A is going to be what are all of the outcomes that are in event A divided by what are all of the possible outcomes in this sample space. So let's take a look at an example with the rolling of the die. So let's now assume that our die is fair again. So that means any one of the 6 outcomes is equally likely to happen. Then let's consider what is the probability that the result of a roll is going to be divisible by 3. So we have our sample space omega, which consists of the outcomes 1, 2, 3, 4, 5, or 6. So the size of set omega consists of 6 elements. Our event A is that the roll is a multiple of 3. I said over here divisible by 3, but keep in mind these are equivalent. If a number is divisible by 3, then that means it's a multiple of 3. So set A over here is going to consist of all of the roles that would be divisible by 3. The roll 3 and the roll 6. So A consists of 3 and 6, and that means A has 2 elements in its set. So therefore, when we're ready to calculate the probability that event A occurs, we can now take the number of elements in set A, which is 2, and divide that by the total number of elements in our sample space, which is 6. So that gives us a proportion of 0.33333 repeating. In other words, 33.33333%. Okay, so let's apply our understanding so far of working with probabilities in sample spaces to the following example. So in the 1970s, research done by Alfred Sommer on vitamin A in night blindness suggested that vitamin A might also reduce childhood death rates. So they were checking to see what effect vitamin A had on night blindness. And at the same time, they were observing what seemed to be possibly a connection between vitamin A and maybe a reduction in the death rate. So in order to test this, children were randomly assigned to 2 groups. One group took a vitamin A pill, so that would be like our treatment group, and another group was given a placebo, and that means a pill that had no vitamin A in it, so typically like a sugar pill, and that would be our control group. And the result of the experiment is organized in what's called a two-way table. So we have 2 variables at play here. Variable 1 is whether or not the child lived or died in the course of that experiment. And variable 2 is our treatment variable, and this is whether or not the child received vitamin A. So here's kind of our treatment that we're looking at. And then we have our response variable, which is whether or not the child lived or died. And from this information, we can calculate several probabilities. And I just want to be sure we're clear how to read a two-way table. So for example, if we consider this row in the two-way table, the very top row, this is telling me information about the children in the study that died. So what I can see here is that 231 children in this study died. Out of those 231, 130 of them did not get vitamin A, and the other 101 did get vitamin A. So this 101 over here, this is corresponding to all of the children that in this study that died and got vitamin A. And similarly, this 130 over here would correspond to all of the children in the study that died who did not get vitamin A. So now that we can read this two-way table, we can answer some questions. So for example, what is the probability that a randomly selected child in the study died? So our sample space in this case would be all 25,200 children in the study. So that's the size of our sample space. And I'm going to assume that all of these participants in the study have an equally likely chance of being picked. So we're going to pick at random. So we're randomly selecting a child in the study. So that means they all have an equally likelihood of being chosen. So what is the probability that a randomly selected child died? Well, we want to calculate what are the total number of children in the study that died divided by the total number of children in the study. So in this case, that would give me 231 were the number of children that died, and our sample space is 25,200. And that works out to a proportion that is 0.0092, or approximately 0.92%. So that's pretty good, considering that here we're looking at what are the probability of that a child died. So that's really, really small. Less than 1% of the children in this study died. Next, we can take a look at what is the probability that a child in the study, randomly selected, got vitamin A. And so here's the vitamin A column. Remember, this first 101 is the number of people in the study that got vitamin A and died. But we want to count all of the people that got vitamin A. So we want to include the children that got vitamin A that died, as well as the children that got vitamin A and lived. So altogether, we can see the total number of children in the study that received vitamin A was 12,991 out of the 25,200. And so taking that fraction gives us 0.5155. So this tells us that approximately 51.55% of the children in this study got the treatment vitamin A, and then the other 49-ish% got the placebo, or in the control group that did not get any vitamin A. Okay, in parts C and D, we now are looking at a compound probability that involves multiple events. So in part C, we want to count up what are all of the children in the study that received vitamin A and died. Both of these things being true at the same time. And recall that was this entry in the two-way table right here. So these 101 children represent children that both got the treatment of vitamin A and died. And that means if we're still picking out of all of the possible children in the study, our sample space is still 25,200. So in this case, in part C, I'll just write part C over here since I'm a little short on space. That's going to be the 101 divided by the 25,200. So this works out to approximately 0.0040. So in other words, 0.4% of the children in the study got the treatment and died. And for the last question, part D, it's asking us what proportion of the children in the study received vitamin A or died. So let's think about this one carefully. So we've got all of these children that I'm circling right here in pink are the children in the study that received vitamin A. So we want to count them. So that's 12,991 out of all of the children, 25,200. And then we also want to include all of the children in the study that died, because we want to count the children that received vitamin A or died. So that would be this total of 231 out of 25,200. But if I stop here, I've made an error. And the error is that there were some children in the study that both got vitamin A and died. And we've included those children in both of these totals. So they're included in this total over here, because this includes all the children that got vitamin A that lived and died. And they're also included in this 231, which was counting all of the children that died, regardless of whether or not they were in the treatment or the control group. And so how many children did we double count? That's exactly these 101 children that were in both of these groups. So I add up the probability that someone received vitamin A. I can calculate the probability that a child died, and then I want to subtract out the 101 children that we counted twice in both of those groups. And you can check, counting this probability gives us approximately 0.5207. So that's about 52% of the children in the study either received vitamin A or they died. And I want to just mention the point of a problem like this might be to determine whether or not we observed any statistical significant difference in the death rates for the children that were in the treatment versus the control group. And in order to do that, we're going to need to explore probability a little bit further in class together to take a look at what are called conditional probabilities. But we'll get to that in class. For now, I just wanted to work through an example with a two-way table that shows how we can calculate some probability.